Hi everybody. In this screencast, I'm going to be going over Gay-Lussac's law, and you should try to follow along as I go through this law with this document, which is 6.5 and in Schoology. So if you go to the 6.5, 6.6 page in Schoology, this document is 6.5. And it's a little data analysis about the relationship between the temperature of a gas and its pressure. And that is what Gay-Lussac's law tells us. Gay-Lussac's law tells us the relationship, the mathematical relationship between the pressure and the temperature for a given gas. And what I'm going to do is I'm just going to show you a little simulation. We're going to gather a little bit of data to show this relationship. So here is a simulation of a gas. Notice we have our particles moving around, and we have a couple metrics that are shown here. We've got the temperature and pressure in the upper right. And for this experiment today, I'm going to hold the volume constant. So we're going to assume that our container is something like a steel container that has a rigid volume that doesn't change. Our first data point is actually right here. So right now, my temperature is 0 degrees Celsius, which if we convert to Kelvin is 273 Kelvin. And if we look at this sample of a gas in the container right now, it has a pressure of 5.3 atmospheres. So you can put that down somewhere, just make a note of that. And what I'm going to do is I'm going to heat this gas up, and we're going to observe what happens to the pressure in the container. So I'm going to try to heat it up to 293 Kelvin. So I'm going to heat my steel container here. 293. Okay, so right now it's at 293 Kelvin, and we can see that our pressure went up a little bit. Our pressure is now at 5.7 atmospheres. So that's another data point right there. The temperature in Celsius is 20, and the temperature in Kelvin is 293, and we have a pressure reading of 5.7 atmospheres, and it went up. And if we see that I heat it up again, this time I'm going to try to heat it to 313 Kelvin, which is like a very hot summer's day. Now we can see that the pressure inside of my container is 6.1 atmospheres. And we can see my particles are moving just a little bit faster too, okay? Moving a little bit faster. Okay, so those are the three data points that we have. 3 temperatures and 3 different pressure readings. And as I add heat, we can see that my particles continue to move faster and faster. That's one of our rules of kinetic molecular theory, that the faster particles move, the hotter the temperature, okay? Okay, so hopefully you had a chance to get those 3 data points. And what I'd like to do now is to go over this table in this little activity here, the Gay-Lussac's law data analysis. So this is the data that we recorded for that little simulation. Notice that I have my temperatures on my left, my temperature in Kelvin over here, my pressure in atmospheres here. But I want to convert that to PSIs. And to convert to PSIs, I will tell you that 1 atmosphere equals 14.7 pounds per square inch. So that's our conversion factor. And so if we're converting to from atmospheres to PSIs, we can do these one at a time. So my first conversion would be a given of 5.3 atmospheres, and I'm converting that to 14.7 PSIs. So I have 14.7 PSI, pounds per square inch, per 1 atmosphere. And when I put that in my calculator, I get 77.9 PSIs, okay? So that would be one data point, and what you can do is you can enter that data point right in the table up here, okay? So this one we said was 77.9 PSIs, okay? And you should do the conversions, and you should try to fill in the pressure in pounds per square inch for each of these 3 boxes. So you'll do a conversion just like I did here, except for 5.7 and 6.1, and you'll fill in the pressure for each of those 3 boxes. And then what you're going to do for this table is you're going to multiply the pressure times the temperature. And you'll do it for here in the first column, you'll do it for the pressure in PSI times the Celsius temperature. And you'll do it for 3 times, one for this row, one for this row, and one for this row. And then you'll do it 3 times here, except this time you'll multiply by the temperature in Kelvin. And then over here, you'll do division, okay? Over here, you'll do division. And the goal here is to figure out a mathematical relationship. Because if these 2 variables are directly related, then their quotient will be a constant. So what we're looking for is we're looking for a constant in one of these three columns. If they're inversely related, their product will be a constant, but if they're directly related, their quotient will be a constant. And the reason we're testing Celsius and Kelvin is because units matter, and we're figuring out which unit it matters here, okay? And that should be enough to complete most of this activity here, okay, and answer most of these questions. For the last part of this activity, it's going to ask you to draw a representation that illustrates the relationship between temperature and pressure. For this particle representation, you should pay attention to a couple things. One is that you're going to draw two 1-liter tanks. So your tank should be the same size. And when you're showing temperature, the longer the arrows on your particles, the faster they are moving. These are vectors. So if you're trying to show that a gas is hotter, you should draw longer arrows. If you're showing that a gas is colder, you should draw shorter arrows. Okay, so that's something you should pay attention to when you draw this particle representation for these gases.